The objective here is to read through a paper by Ulrich Drepper titled What Every Programmer Should Know About Memory, and I'll have to split it up into a few parts because it's 114 pages, but I thought it was a really great reading and just thought I'd come up with a video to put into the research reading series, breaking the big ideas apart. Now, at times this paper gets really technical. I don't want to do that. I want to keep this pretty lighthearted and just try to make technical information pretty entertaining to learn. And some of this information will be a little dated because the paper came out in 2007. This is when the Rockies played the Red Sox in the World Series. The Colts were playing the Bears in the Super Bowl, and the Spurs were playing the Cavs, demolishing the Cavs in LeBron's first finals appearance. And I know not all techies are into sports like I am, but I like to do this little association. When I think of these kind of sporting events, I remember exactly how long ago that was. So that's just what I'm trying to emphasize here. 2007, that's quite a long time ago. The date of this recording is in August 2019. So when I start talking to you about the North Bridge and South Bridge, you're going to have to take that with a grain of salt. So what I mean by that is take that while maintaining a degree of skepticism about its truth, because if I'm talking North and South Bridge, if I'm talking about processors that are old, sure, a lot of this still applies, but it's not going to be true for the newest of processors. Or I should really say the newest of DRAM modules out there, because that's what this paper is focusing on. I just did a huge series on CPUs, now I'm trying to learn more about the RAM. So to summarize this first paragraph, the abstract, that is the most important of all paragraphs, basically memory accessing RAM, is the new biggest bottleneck in a computer system. First sentence of the introduction reads, in the early days, computers were much simpler. The various components of a system, such as the CPU, memory, mass storage, and network interfaces, were developed together, and as a result were quite balanced in their performance. But now we're getting into an age of specialization, and some things progress faster than others. The slowness of mass storage has mostly been dealt with using software techniques, that is, operating systems keep most often used and most likely use data in main memory, which can be accessed at a rate orders of magnitude faster than the hard disk. Nothing new about this, but something maybe less well known about is caches. Cache storage was added to storage devices themselves, which requires no changes in the operating system to increase performance. And so we get our little one footnote right there. It says changes are needed, however, to guarantee data integrity when using storage device caches. So the first question in our new series here, titled WEPSKAM, as in what every programmer should know about memory. So the first question of WEPSKAM is, what problem exists when using device caches? And the answer is right there, data integrity. Now this reading will be a little tougher because we got to keep jumping back up and to the right, but this is a nice summary right here of the overall changes systems are going through. So RAM hardware design, that is changing in both speed and parallelism. Memory controller designs are changing, and that gets really fascinating, the tricks they come up with to improve memory access by manipulating the memory controller. More on that later. Another change is in CPU caches, and there's so many different types of caches out there, and it gets confusing. And then here's one of our older concepts, and I'm still trying to figure out exactly how much it's not used anymore, or if there's just a new way to think about this, but I'm talking about direct memory access. That's kind of a tricky topic, but I'll elaborate on that later. Just know that when it comes to operating systems, specific details and solutions in this particular text will be exclusively Linux. And I don't know how many of you love Linux as much as I do, so I'm happy to read that news. And it's not surprising if this is a Red Hat thing. Okay, so note to myself here was just skip this page, because of course you got your thanks and about the document structure. I always thought it's funny to, when you're reading technical things or just things in general, and they constantly tell you what they're about to tell you, and I'm like, why don't you just tell me it already? So here's the first thing they tell me, is that the commodity market is the king here. It is more cost-effective to use many smaller connected commodity computers instead of a few really large, and exceptionally fast systems. Red Hat, as of 2007, expects that for future projects, the standard products, not projects, sorry. The standard building blocks for most data centers will be a computer with up to 4 sockets, each filled with a quad-core CPU. That is the case that in the case of Intel CPUs will be hyper-threaded. So number 2 footnote says, if we go down there right away, hyper-threading enables a single processor core to be used for 2 or more concurrent executions with just a little extra hardware. So let's break those two concepts down into questions. First, what type of CPUs would data centers most likely have? The answer will be quad-core CPUs. And if you're looking at the word sockets there, the computers themselves in the data center, the servers themselves, will have up to 4 sockets. So 4 sockets with 4 quad-core CPUs gives us how many cores total? 4 times 4 is 16. So there you go, a lot of cores. And to be a really good student and explain fully, you would say that those quad-core CPUs will also be hyper-threaded. So then my question is, what is hyper-threading? Okay, so if we come down here, rather than all those fancy words, I would say something like, hyper-threading is when multiple cores can execute different instructions at the same time. The whole idea is concurrent executions. Alright, so go back to where we left off. The next sentence was a good one. It says, this means the standard system in the data center will have up to 64 virtual processors. Bigger machines would be supported, but the quad-socket, quad CPU core case is currently thought to be the sweet spot, and most optimizations are targeted for such machines. So your research question of the day will be to see if this is still true. So is the quad-socket, quad-core still the norm in data centers today in 2019? If we look down here, they have a nice little image for us. So we got 2 CPUs communicating to a north bridge, which communicates to a south bridge. North bridge is talking to RAM, south bridge is talking to any devices or any cards on the PCIe slot or plugged into the USB. Oh, and don't forget our SATA cable there, connected to the hard disk. But according to Stack Overflow, this whole North Bridge concept is gone in 2015. So with that said, we'll actually skip quite a few details right here. Let's jump up to the fact that today PCIe Express, SATA, USB buses are very important, but PATA, and the IEEE 1394 serial and parallel ports are also supported by the South Bridge. And I just had to take you to Stack Exchange to see this. So here you go. There's an old CPU, clock generator. We got our North Bridge and South Bridge. But apparently this is 2015 and older. The new architecture in town is this whole platform controller hub, aka PCH. So to squeeze a question out of this, what plugs into the PCH? And then for bonus points, go ahead and say the platform controller hub, and then you can write your answer from there. And since we're talking about like not anymore concepts, here's a list of them. All data communication from one CPU to another must travel over the same bus used to communicate with the North Bridge, so that's not going on anymore. Now CPUs, cores will need to talk to each other, but we'll get to that later. The next one is all communication with RAM must pass through the North Bridge. After that, the RAM has only a single port. I had to put question marks on that one because I just don't know if that's true. It might very well still be. And our last one here is communication between a CPU and a device attached to the South Bridge is routed through the North Bridge. So I guess we could just stare at that picture all day and really try to wrap our minds around what's going on with the processor communicating with the PCH. I see system memory right over here connected directly to the processor, so we'll get to that stuff later. But for now, this next paragraph, if I was to summarize, is just all about that direct memory access. Then they're going to go into DDR2. DDR2 doubles the available bandwidth, so that's the 2 maybe. Plus, I guess the fact that it's the second version of DDR. When we get to page 8, we'll be able to read a lot more about that. Let's take note of FB DRAM being here. So there's all these different DRAM types. But I'm trying to speed you along here while staying pretty true to the order of the book. So this paragraph I thought was noteworthy. There is more to accessing memory than concurrency, however. Access patterns themselves also greatly influence the performance of the memory subsystem, especially with multiple memory channels. If we go right back up here, this literally said, recent RAM types require 2 separate buses or channels. So think of buses when you think of channels, as they are called for DDR2. Okay, so let's gather ourselves, ask some questions. The text asked or brought up concurrency. So let's see what you can find on that. What is concurrency? And the next one is, what are... Now the text says section 2.2, we'll go into that. Okay, so we could be patient. Let's go back up to the concurrency idea. I mean, the regular English definition is actually pretty good. The fact of 2 or more events or circumstances happening at the same time. If you want the computing one, then here it is, the ability to execute more than one program or task simultaneously. So what were they saying about concurrency? There's more to accessing memory than concurrency, so as you can imagine, there would be a need to access more memory if you're concurrently running something. But according to Drepper here, there's more to it than that. So we have our dated picture right there. This paragraph talks about the advantage of having more than one memory bus, because therefore your total memory bandwidth will increase. So he's speaking very highly of the Northbridge of Intel for having a Northbridge, it looks like. Now I like memory controllers, and they say that using multiple external memory controllers is not the only way to increase memory bandwidth. But if I'm understanding my 2019 research correctly, it's a dang good way to increase memory bandwidth. But you gotta do some tricks. This paper, though, says that one other increasingly popular way is to integrate memory controllers into the CPUs and attach memory to each CPU. So we'll be learning about SRAM here in a moment. But maybe that's not what he's foreshadowing here, because he goes on to say this is made popular by SMP systems based on AMD's Opteron processor. So figure 2.3 is right here. We can see a missing Northbridge, right? And what is an SMP system? SMP involves a multiprocessor computer hardware and software architecture where 2 or more identical processors are connected to a single shared memory. They have full access to all input and output devices and are controlled by a single operating system instance that treats all processors equally. And then just know most multiprocessor systems today use this architecture. And for your average user, though, we're not multiprocessor so much as we're multi-core, which the architecture would then apply to the cores, they say. And I'll just leave this topic with the diagram you can see here. Each processor seems to get its own cache. So coming back to the paper, we got to wrap this up. This is long enough for the first video. With an architecture like this, there are many memory banks available as there are processors. Going to the top here, it says the disadvantages to this architecture. First, because the machine still has to make all the memory of the system accessible to all processors, the memory is not uniform anymore. Hence, you're going to see this word a lot if this is a topic you're studying, but it's called, or it's NUMA, non-uniform memory architecture. So what is the disadvantage to SMP architecture? So to better illustrate this, let me go back to that picture. It's saying, okay, we got our 4 connections to 4 types of RAM, right? It's saying that in this case, the interconnects between the processors have to be used. So I drew circles around these because it's tough, right? So if this CPU2 needs something from RAM, this RAM, it's got to go through that line. Or even worse, I hope not, it would have to go through these 3 just to get to where it's supposed to be. So that's NUMA in a nutshell. Each such communication has an associated cost, and we talk about NUMA factors when we describe the extra time needed to access remote memory. So they explain that there's 2 levels for each CPU. As you saw in the picture, you have a CPU that's immediately adjacent to the RAM that's needed, and then you'll have one which is 2 interconnects away. Alright, so picture's worth 1,000 words. Again, using our example, here is one interconnect, if you can see where my mouse is, and here is the second one. So the fastest would be through 2 interconnects. Or I mean the slowest. The fastest would be if the CPU 1 needed this one, it's only 1 interconnect and everything's all good. Now, this isn't the only architecture out there. There's the IBM X445 and SGI's Outex series. You should just be aware that this is not the only design we can go with. But commodity NUMA machines exist today, and it will likely play an even greater role in the future, they say. It is expected that from late 2008 on, every SMP architecture, every SMP machine will use NUMA. The costs associated with this makes it important to recognize when a program is running on a NUMA machine. So this is the perfect place for us to end. Why, as programmers or wannabe programmers, do we need to know this stuff? Because if your programs are running on a NUMA machine, there's going to be cost to the way you design and write your program. So thus, this is just part of what every programmer should know about memory.